Hearty welcome to today's class. Last class, we were discussing about the introduction of liquid state. Today, we are dealing with molecular interactions in liquids. Here, we will discuss different interactions in liquids. We know that molecules in the liquids are arranged not very closely. There is some empty space between the liquids. Because of this empty space, there are some interactions in between the liquids. So, as we saw in the introduction, the molecules are arranged like this in liquids. And as we see here, the molecules are having some space, in between some spaces are there. Therefore, there are some interactions in between the liquids. There are attractive forces and repulsive forces in liquids. We know that the positive and negative charges will attract each other, or positive negative charges will attract. That means the unlike charges will attract and like charges will repel. That means if we have positive and negative charge and negative and positive charge, they will have an attraction. And if there is like charges, that is positive and negative, there will be repulsion between themselves. This principle is applicable in the case of molecular interactions in liquids. As we saw in the introduction, in the case of liquids, there are some empty spaces between the liquids, and because of these spaces, empty spaces, and the molecules are arranged like this, there are some interactions in the case of liquids. And when we see the interactions in liquids, these molecular interactions are not so strong as ionic and covalent bonds. We know that the ionic and covalent bonds are so strong. That are the things which some molecules are held together by this ionic and covalent bonds. In the case of liquids, these molecular interactions are not so strong as ionic and covalent bonds. Therefore, the different molecular interactions in liquids are attractive intermolecular forces. They are nothing but van der Waals forces, and second one is repulsive forces. Different molecular interactions in liquids are attractive forces and repulsive forces. When we say attractive forces, as we seen last class, because of the arrangement of the molecules in the liquids, there will be an attractive forces between the molecules in liquids. And these attractive forces in liquids are also known as van der Waals forces. And here, these attractive forces only helping the liquids for the different properties like viscosity, cohesion, surface tension, and boiling point. This force is named after the Dutch physicist Jonas van der Waals. These attractive forces in liquids are also known as van der Waals forces because the scientist Jonas van der Waals studied about the attractive forces in liquids. The attractive interactions in liquids are responsible for cohesion, viscosity, surface tension, and boiling points. The cohesion is nothing but the strong attractive forces in the liquids, and viscosity is nothing but the resistance to flow. Surface tension is the surface phenomenon, that is the surface molecule is pulling towards the interior, and because of that there is a tension is happening at the surface of the molecule, that is called as surface tension. And boiling point is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. So, all these properties, cohesion, viscosity, surface tension and boiling points are responsible. The responsible thing for all these properties are attractive forces in liquids. Now, let us see the different types of attractive forces. The different types of attractive forces or van der Waals forces are, the first one is dipole-dipole forces, the second one is dipole-induced dipole forces, and third one is induced dipole forces. The dipole-dipole forces, as the name says, the dipole-dipole forces are the attraction forces between the two dipoles, and dipole-induced dipole forces are the attraction forces between one dipole molecule and the another induced dipole molecule. And induced dipole forces are between the two nonpolar molecules. Okay, so here let us see each one by one. Here the dipole forces are attractive interactions between polar molecules. Then dipole-induced dipole forces is the second one. This is the attractive interactions between polar and nonpolar molecules. Here the nonpolar molecules are becoming the polar molecule and there will be an attraction. That is why this attractive force is called it as dipole-induced dipole forces. And the third one is induced dipole forces, or it is having other names like dispersion forces or Langton forces. We saw this force in our introduction session in brief. Here we will see detail what is induced dipole and induced dipole forces. And this induced dipole and induced dipole forces are the attractive interactions between atoms or nonpolar molecules. Okay, here we have three different types of attractive forces, and the first one is dipole forces, second one is dipole-induced dipole forces, and third one is induced dipole forces. Now, first we will see what is dipole forces in detail. Okay, as the name say, here the interaction, the attractive forces between two polar molecules. Dipole forces means the interactions between two polar molecules. That means the polar molecules are having dipole moments, or the molecule that possess permanent dipole moment are called polar molecules or dipoles. The molecules that possess permanent dipole moments are polar molecules or dipoles. For example, if we have an HBr, here this Br is more electronegative than this hydrogen, therefore it is having this bromine is getting partial negative charge and this hydrogen is getting partial positive charge. Here there is a separation of charges between hydrogen and Br. Therefore, this HBr or hydrogen bromide is a polar molecule, or this molecule possesses dipole moment. Okay, now when this molecule, when we take this molecule, this hydrogen is having partial positive charge and this bromine is having partial negative charge. And this charge, this partial negative charge and partial positive charge is always less than that of the unit of electronic charge. We know that the unit electronic charge is 1.6 into 10 power minus 19 coulomb. That is 1.6 into 10 power minus 19 coulomb. So, the charge of this charge is less than that of this partial negative charge is less than that of 1.6 into 10 power minus 19 coulomb, and this partial positive charge also less than that of 1.6 into 10 power minus 19 coulomb. And this term is first coined by the scientist W.H. Keesom. W.H. Keesom. Therefore, this dipole force is having another name called Keesom forces. This dipole forces is having another name called Keesom forces because this force is studied by the scientist W.H. Keesom. Now, let us discuss about how the interaction happening in molecules. Dipole-dipole interaction is happening between two molecules. So here we have an example of HCl, which is here. Again, I am writing here. Here we have an example of HCl, and this hydrogen is getting partial positive charge and this chlorine is getting partial negative charge. And this hydrogen molecule is having a nearby hydrogen chloride. This HCl here, this hydrogen is getting partial positive charge and this chlorine is getting partial negative charge. When this hydrogen chloride is coming in contact with this hydrogen chloride, what will happen? There will be an interaction between the positive charge and the negative charge. Therefore, the interaction is happening or the attraction is happening between this HCl and this HCl. Here it is showing that is there will be an interaction between this HCl that is polar and this HCl that is also polar. Therefore, dipole-dipole interaction is between two polar molecules. And the strength of this force is range from 5 kilojoule to 20 kilojoule, and this force is less than that of the force which we have in covalent bonds or bond dissociation energy. That means we know that we understand that these dipole-dipole interactions are weaker forces when we compared it with covalent bonds. Then this dipole-dipole interaction force is also less than that of or it is weaker than that of iron-iron interactions and iron dipole interactions. Iron-iron interactions and iron dipole interactions. So, these dipole-dipole interactions are weaker than that of covalent bonds. It is also weaker than that of iron-iron interactions and iron dipole interactions. Now, let us see the energy of the dipole-dipole interaction. Here, the dipole-dipole interaction energy depends upon the dipole moments of the polar molecule. That means, what is the polarity of that particular molecule? That depends upon the energy of the dipole-dipole interaction. That is what here the interaction energy, the potential energy V of dipole-dipole interaction depends on the dipole moments of the interacting dipoles. And this interaction energy depends upon the Kelvin temperature, that is T, and the sixth power of the distance r between the dipoles. The potential energy is inversely proportional to the temperature Kelvin and the sixth power of the r, that is the distance between the two polar molecules. Here we have the equation to find out the potential energy of molecules which are having dipole-dipole interaction. V is equal to minus 2 by 3 kT mu1 mu2 divided by 4 pi epsilon 0 into 1 by r power 6. Here mu1 and mu2 are the dipole moments of two polar molecules and epsilon 0 is the permittivity in space and K is Boltzmann constant, and T is the temperature in Kelvin, and R is the distance between the two polar molecules. The dipole-dipole interaction. The strengthness of dipole-dipole interaction or the magnitude of the dipole-dipole interaction depends upon the polarity of the molecule. And in the equation we have a negative sign. The negative sign indicates that the attraction only shows this negative sign. If the molecule has more polarity, then the magnitude of the potential energy also will be high. And this dipole-dipole interaction is having some applications, or it has some influence on the physical properties of liquids. That is, if the molecule is having greater dipole-dipole forces, then the melting and boiling points of that substances will be higher. That we will see by some examples. Here we have an example of nitrogen and oxygen. Here this nitrogen and oxygen is having a boiling point of minus 196 degrees Celsius and minus 183 degrees Celsius respectively. Here this nitrogen is non-polar. That means if you take nitrogen, the electrons are shared between these two nitrogen atoms. Therefore, the dipole moment is 0. And in the case of oxygen also same. Here the electrons are shared by two oxygen atoms. Therefore, the dipole moment is 0. Otherwise, we can see that this nitrogen and oxygen are non-polar molecules. Since they are non-polar molecules, their boiling point is low, that is minus 196 degrees Celsius and minus 183 degrees Celsius respectively. And then if we take another example like NO, here the NO is having slight polarity, therefore there is some increase of boiling point, that is minus 151 degrees Celsius. Here this NO is having a slight higher boiling point, that is minus 151 degrees Celsius. This NO is having definitely the separation of charges, because here the oxygen is having partial negative charge and this nitrogen is having partial positive charge, because oxygen is more electronegative than nitrogen. Therefore, since NO is having separation of charges and dipole, it is polar, and because of that this NO is having a slight increase of boiling point compared with the non-polar molecules. And another example is more HCl, more polar HCl, or the HCl molecule. As we saw earlier, this is polar molecule, and here this chlorine is partial negative charge and this hydrogen is partial positive charge, and here the dipole-dipole forces are higher. Since the dipole-dipole forces are higher, this HCl is having higher boiling point, that is minus 85 degrees Celsius. Okay, this is about dipole-dipole forces. So, this is the dipole-dipole forces is the first category of the attractive forces in liquids. Here this dipole-dipole forces are between the interactions of two polar molecules, and this dipole-dipole interaction depends upon the magnitude of the polarity or magnitude of the dipole. Dipole moment means molecules that possess permanent dipole moment is called it as polar molecules or dipoles, and here the energy depends upon it is inversely proportional to the temperature and sixth power of the distance between the two molecules. And the force, these dipole-dipole forces are weaker than the covalent bond which we have, and it is also weaker than the iron-ion interactions and iron-dipole interactions. I hope you understood what is dipole-dipole interactions. Now, let us see the second type of attractive forces, that is dipole-induced dipole forces. As I said earlier, these dipole-induced dipole forces are between the interactions of the polar molecule, between the polar molecule and non-polar molecule. So, you will be curious about how this non-polar molecule are having an interaction with the polar molecule. Let us see what is happening here. In the case of dipole-induced dipole forces, we have a non-polar molecule. If you take the example of water, that is polar, and this water here, this water molecule, this oxygen is having partial negative charge, and this hydrogen is having partial positive charge, and this hydrogen is having partial positive charge. And here there is a separation of charges, and this water molecule is polar. And if this molecule is a permanent dipole moment molecule, and we have another molecule, isolated molecule, oxygen molecule here. And this oxygen molecule is non-polar because the electrons are shared between two oxygen atoms. Because the electrons are shared between the two oxygen atoms, this oxygen molecule is non-polar. Now, let us see how this interaction is happening between this water molecule and this oxygen molecule. Here, this water molecule is having an interaction, the isolated oxygen molecule is having an interaction with this permanent dipole. How it is happening? That is our question. That is, the electron cloud of this oxygen molecule is getting cancelled by the effect of this water molecule. That means when a polar molecule gets near a polarizable non-polar molecule, that is what oxygen molecule, the polar molecule produces an electric field, and because of the electric field of this water molecule, the electron cloud of the non-polar molecule is getting distorted. So, because of the electric field of the water molecule, the oxygen molecule's electron cloud is getting distorted. So, since the electron cloud of the oxygen molecule is getting distorted, what is happening? It is getting a separation of charges. Here this oxygen is getting partial negative charge, and here this oxygen is getting partial positive charge. That means the oxygen molecule, this isolated oxygen molecule is now polar, or it is getting a dipole. That dipole is called it as induced dipole. That means this dipole is induced by the molecule, water molecule. Because of the electric field of the water molecule, the electron cloud of the oxygen molecule is getting distorted, and this oxygen molecule is becoming a polar molecule or a dipole molecule. There will be an interaction between this oxygen molecule and water molecule. This is what happening in the case of dipole and induced dipole interactions. Let us see another example. I hope you understood the case of water molecule and the interaction of water molecule and oxygen molecule here. Now let us see another example, that is the interaction of hydrogen chloride and argon. Here we have hydrogen chloride, and this hydrogen chloride is polar. That means there is a separation of charges. Here chlorine is having partial negative charge and hydrogen is having partial positive charge. That means this hydrogen chloride is polar molecule. And another molecule is here, that is argon. that is nonpolar molecule, and this nonpolar molecule is getting a dipole because of the electric field of the hydrogen chloride. Because of the electric field of the hydrogen chloride, the electron cloud of the argon is getting distorted, and this argon is getting a dipole, or this nonpolar argon will become a polar molecule now, and therefore here there is a partial positive charge and here there is a partial negative charge. Then there will be an interaction between hydrogen chloride and argon. This is what happening in the case of dipole and induced dipole interactions. Here, the strength of the dipole and induced dipole interactions depends on two factors. I hope you might have understood the factors which affect the dipole and induced dipole forces better than me now. That is, one is the polarity of the polar molecule. That means if HCl molecule or the polar molecule is more strong, that molecule can distort, the electric field of that molecule can distort the electron cloud of the another nonpolar molecule. Second thing is the polarizability of the nonpolar molecule. That means how fast this nonpolar molecule can distort by the effect of the polar molecule. That is the polarizability of the nonpolar molecule. So, two factors which affect the dipole-induced dipole forces. One is the polarizability of the nonpolar molecule. Second thing is the polarity, the high polarity of the polar molecule. Then the next thing is that if the nonpolar molecule, if the nonpolar molecule is large, here if the nonpolar molecule which we take is large, then there will be an easiness to distort the electron cloud of the argon. If there is an easy to distort the electron cloud of the argon, then the interaction that fast it can become a induced dipole molecule. Therefore, there will be an interaction, induced dipole interaction very fast. Here also, the interaction energy V is inversely proportional to the sixth power of R. The interaction energy V is equal to minus mu1 square alpha 2 divided by 4 pi epsilon 0 into 1 by R power 6. Here this mu1 is the dipole moment, the alpha is the polarizability of the nonpolar molecule, epsilon 0 is the permittivity of space. The application is the slight solubility of oxygen in water is due to dipole-induced dipole interactions. So, the solubility, the slight solubility of oxygen in water is due to dipole-induced dipole interactions. I hope you understood what is dipole-induced dipole interactions in liquids. Now, let us see the third attractive interactions, that is induced dipole forces or dispersion forces or Lenten forces. As the name says, this interaction is between two nonpolar molecules, that is the induced dipole and induced dipole forces. Here we have a nonpolar molecule and here also we have a nonpolar molecule. Okay. As we know, all molecules are in motion and particular time there will be a separation of charges. That means the nonpolar molecule will become polar molecule. The nonpolar molecule has become polar molecule now. That means induced dipole. Now what will happen? The same thing what we discussed there in dipole-induced dipole forces, that is here the electric field of this induced dipole molecule or the polar molecule will distort the electron cloud of the nonpolar molecule. When it distorts the electron cloud of the nonpolar molecule, what will happen? Here this nonpolar molecule are also getting the separation of charges. Therefore, then this nonpolar molecule also become polar or induced dipole. This nonpolar molecule also become polar molecule or induced dipole molecule. Here this also induced dipole. Now both the nonpolar molecules are induced dipole molecules or polar molecules. Now there will be an interaction between the negative charge of this non-polar molecule, induced dipole molecule, and the positive charge of this molecule. Therefore, there will be an interaction between these two non-polar molecules. I hope you understood. This induced dipole forces are between two non-polar molecules. Since these induced dipole forces are studied by the scientist Fritz London, this is called it as London forces. And this induced dipole forces are the weak attractive forces compared to the dipole forces and dipole-induced dipole forces. Among these three, this induced dipole and induced dipole forces are the weak attractive forces in liquids. And here the energy which is generated in the case of induced dipole forces, induced dipole and induced dipole forces are in the range of 1 to 10 kilojoule per mole. 1 to 10 kilojoule per mole, that is the weakest among the intermolecular forces. The magnitude of this induced dipole and induced dipole forces depends upon the polarizability of the atoms or molecules. Here we have two nonpolar molecules, and which molecule are getting here two nonpolar molecules are there, and how fast one can distort the electron cloud of the other. Like that the polarizability the polarity is getting, or the actual magnitude of this induced dipole and induced dipole forces depend upon the polarizability of the atoms or molecules. Here also the energy depends upon the 6th power of R, and the equation for the dispersion forces or induced dipole forces is V is equal to minus 3 by 2 alpha 1 alpha 2 I1 I2 divided by I1 plus I2 1 by R power 6. Here the alpha 1 and alpha 2 are the polarizabilities of two nonpolar molecules, and I is the ionization energy. Ionization energy is nothing but the energy which is required to remove an electron from the isolated atom or molecule. Ionization energy is the amount of the energy required to remove an electron from the isolated atom or molecule. From this equation, we can understand that this induced dipole and induced dipole forces depends upon the polarizability of the molecule and ionization energy of the molecule. And here also the negative sign indicates the attraction forces. And these weak attractive forces constitute a major fact in the sample of oxygen or nitrogen or noble gases. When we look into our periodic table, especially in the case of noble gases, that is fluorine, chlorine, bromine and iodine. Here this fluorine and chlorine are gases, and this bromine is a liquid and this iodine is a solid. And when we see when we see these gases, the boiling point of these gases, the boiling point is increasing while we come down to group, or when we move down the group, the boiling points are increasing. The reason to increase the boiling point is because of the induced dipole forces or Lenten forces. That means the iodine is large. Since iodine is large, it is very easy to distort the electron cloud of the iodine. Therefore, the induced dipole forces or Lenten forces are acting in the case of iodine, easy to act in the case of iodine. Therefore, iodine is having high boiling point compared to the fluorine, chlorine and bromine. I hope you understood induced dipole and induced dipole forces. So, till now we were discussing about the different attractive forces in liquids. They are dipole forces, induced dipole forces, induced dipole and induced dipole forces. So, I hope you understood all these attractive forces. Now we have another force, that is repulsive force, that we will discuss in our next module. Thank you.